Okay, welcome back everybody to the Python tutorial seminar series. Today, Max Grover will be covering Intake-ESM. So before we begin, we have to review the code of conduct. By joining this Zoom call, you've agreed to adopt these values and engage in respectful communication only. Any disrespectful or inappropriate remarks will have you removed from the chat. From the call by one of our co-hosts. The seminar is only an hour long, so if you have trouble, people will try to help you in the chat, but ultimately there's not much time for individualized attention and we'll have to get you up to speed afterwards, and we will do our best, so please relax and learn all that you can. Your speaker today is Max Grover. So Max works as a software engineer at the Climate and Global Dynamics Lab here at NCAR. Graduated with a BS in meteorology from Valparaiso University. Am I saying that correctly?
Yeah, Valparaiso.
Valparaiso, and will complete his MS in atmospheric science this spring at University of Illinois, Urbana-Champaign. So congratulations, Max, on that. That's a lot of work. He works on Python-based tools to support climate model evaluation and contributes to the Earth System Data Science Initiative, or ESDS. His research in graduate school focused on using observational data collected during the Relámpago cacti campaign in Argentina to study mesoscale convective dynamics, primarily utilizing mobile radar observations as well as GOES-16 satellite imagery. So Max also took part in our SciParks internship, or no, in the Unidata internship in 2019. So has some connections to UCAR before he began working here, which is great. On a fun note, Max likes hiking, breweries, and spending time in the water. His summer job before this was working at a resort in southern Wisconsin as a tour boat captain. That's very cool. And has over 40 Hawaiian shirts. So if anyone can top that, I would love to hear your number in the chat. But if you don't have time to count them now because of the tutorial, that's fine. So some resources for today, as always, Stack Overflow, the Intake-ESM documentation, always a good place to look, and today's content, which is I'll make a small note, we have a new GitHub organization, Project Pythia Tutorials, and then each tutorial seminar from now on will have its own repository within this organization. So hopefully that makes it a little easier for you to find each session's content moving forward. And with that, I will pass the baton to Max.
Ready? Thanks so much, Julia. Thanks for the introduction. I'll go ahead and share my screen and we can get started. Alrighty, so if you haven't done so already, go ahead and clone this repository. So it's within the Project Pythia Tutorials and Intake-ESM tutorial with today's date. We can go ahead and copy that. We'll go ahead and get clone. All right, so you can see we cloned that. And then let's go ahead and move into that directory. At this point, you'll see within this directory, we have the README, data, the environment, and the tutorial directory. So we need to set up our environment first. So we'll do conda env create-f environment.yaml. And we can go ahead and let that run while I go ahead and introduce today's topic. So I'll start with some slides to kind of provide an overview of this project and this package. And then we'll go ahead and get to some live coding. So go to presentation. So again, today's tutorial is focused on Intake-ESM. So some sort of overall motivating factors for Intake-ESM. So Intake-ESM's goal is to make it easier to find data, load data into your analysis, and make your analysis workflows more extensible so you can apply your analysis code across whatever different cases you're looking at. And essentially, this provides a data catalog, which is searchable. It abstracts the file access. So So it doesn't matter if you're working with, say, NetCDF or even CSV or say ZAR file format, for example, sort of abstracts that step away. And it makes it easier to apply your analysis code to different use cases. So say, for example, you're working with some climate model data and you want to look at multiple different cases. It helps to sort of abstract so that we don't have to necessarily load in those files by hand. And then today's example we'll be using is the CESM1 large ensemble. So I'll kind of provide an overview of the CSM large ensemble, and again, we'll sort of dig into some of the code here in a bit. But this data set is relatively complex. We have two different spatial grids within this data set: land, atmosphere, and the ocean ice. Multiple vertical axes. So we have surface data, three-dimensional atmosphere, three-dimensional ocean, varying temporal frequencies and resolution. So we have monthly, daily, and 6-hourly data, multiple time axes. So the 20th century, RCP85, which is a future scenario, and so on. There's a total of 40 ensemble members. So how can we help people access this data? So we can help people find which components, frequency, or experiment they're looking for, and we can make it easier to load this data into an X-ray data set. So that way they can get to analyzing and kind of looking at more of those scientific results instead of having to worry about the underlying data. So that first part of Intake-ESM, intake. So intake is sort of this larger project. So it's a larger package and / ecosystem. So intake is a lightweight package that allows data as declarative code. And so this provides a consistent API, preventing the need to know the backend library. It focuses around the core data model of X-ray data sets. It provides extensible cataloging, transparent access to group data and catalogs for different data formats. So for example, CSV, NetCDF, ZAR, and so on. It's relatively minimalist. So it provides an extensible plugin, which is where Intake-ESM plugs in, or Intake-ESM plugs in. So Intake-ESM is a plugin within this ecosystem that's made to work with Earth system model data. So for example, the community Earth system model developed here at NCAR, or say the CMIP6 or CMIP5 collections, it's really made to work with this Earth system model data and make it easier to both search and access. So Intake-ESM works around this core idea of a data catalog. And so there's two components to this catalog. First off, there's this ESM collection file, which is a JSON file that provides metadata about the catalog. And so the specification for this JSON can be found within this ESM collection spec. But basically it provides some overall information about the catalog, what to merge together, and some sort of overarching metadata. And then the second file is a catalog file, which is a CSV or a compressed CSV that lists the catalog's contents. So this file includes one row per dataset granule. So an example of that would be, say we had some community Earth system model CSM data where we had these time series files with temperature from say 1990 to 1995. That would be sort of one data set granule. So it's each kind of core asset within each row. And then the columns in the CSV must match the attributes and assets within the ESM collection file. So these catalogs can be built using this ECG tools package. So this makes it a little bit easier to be able to build some of these catalogs. There's also quite a few catalogs available, both on NCAR's HPC system as well as cloud available catalogs. So let's take a look at one of these collection files, or this JSON. So we'll see here. So at the top here, we have the ID. So this is the name of the catalog. We have a description of the catalog. the path to the CSV. So this is the actual table with the values. And then we have these attributes, which line up to each column name within the CSV or the table. So we see, for example, component, you can imagine stream and other sorts of columns. And then finally, the path. And then we also have to specify the format here, which in this case is ZAR. Also within this file is the aggregation control. So this is telling Intake-ESM what it's going to merge across. And feeds this into Xarray. So we can see here we're looking to merge on the component, experiment, and frequency, which are these group by attributes. And then we're also going to aggregate across variables. So we want similar, so say we had a temperature and specific humidity from the atmosphere. We want those to be in the same data set if they share this component, experiment, and frequency. And we'll dig into this a little bit in terms of a real example of using this, but this is what the JSON looks like. And then with that JSON also comes this CSV. So this is a pandas representation. So this is basically just a table of values where we can see the individual assets. So this path lines up to a ZAR store that's stored on Amazon. We can see the start and end time of this data set, units, the spatial domain, vertical levels, frequency, experiment component, long name, as well as the variable name. So this is the accompanying CSV. So these two, the JSON and the CSV, are closely tied together. So at this point, let's go ahead and go back to our terminal. You'll see that our kind of environment is all ready to go. So we can just go ahead and activate that. And then we will call Jupyter Lab, which will open up a Jupyter Lab environment. So you can see that firing up. So over here, go ahead and get started. So you'll notice within, so this is within the tutorial directory. So this, you click on tutorial, and then you'll see this Intake-ESM 1. So this notebook includes the entire sort of narrations. We have the title here, sort of an overview. It's recommended prerequisites. So if you, after this tutorial, if you're interested in digging into more to Xarray and matplotlib, that could be helpful. And then within this notebook, we actually executed all the cells and added some additional narration. For the sake of this tutorial, I'm going to go ahead and open up this blank one, which will hopefully make it easier for everyone to sort of follow along and do some live coding. But after the fact, if you're interested in a little bit more explanation, or maybe a little bit want to catch up on stuff, you can definitely go back through here and take a look. So I'll kind of provide again this overview of what exactly Intake-ESM is, how we can use it to read in data, why and how do we work with dictionaries, data sets, and then how to write some sort of quick analysis code with Intake-ESM. So we'll start off with their imports. So we'll import intake. You'll notice that we're not calling import Intake-ESM. That is because Intake-ESM is a plugin. So once we call import intake, that comes with Intake-ESM. You also notice that we're importing distributed, which is Dask distributed. And from that, we're grabbing the client as well as the local cluster. We're also importing Xarray, matplotlib, and then fspec, which is a tool to work with different files. So let's go ahead and do that. Second to import those. And then also, if you're interested in running this from a binder environment, you can do that by going to the main GitHub repository here and clicking launch binder, this will launch this Jupyter lab environment for you. So you don't necessarily have to download this locally. So see, we have our imports, and then we also have our Dask cluster spun up. So we can go ahead and clicking on this link here. This is the dashboard link. We can take a look at our cluster. So you'll see we have 4 workers here. We have 16 gigabytes of memory. I won't dig into the dashboard too much. We'll basically just go back to it just to make sure things are running and we have our processes running. But basically, this is just allowing us to run in this distributed system and work more in parallel. So as mentioned before, we're going to look at data from the NCAR large ensemble, which is hosted on AWS. So this first line, so this is setting up this file system, which is basically essential to doing Globe on your local file system. It basically just provides you to ability to take a look at what's in that bucket. So we see within this bucket that we have a few different directories. So we have this atmosphere, we have catalogs, we have ice northern hemisphere, ice southern hemisphere, land, and oceans. This is all separated by the individual components. So let's look inside one of these. Let's go one step further. So look inside one of these, and we see that we have daily, we have 6 hourly data broken up across those 3 different year ranges. We have monthly data, and then static is where the grid's at. So we don't necessarily see our data files yet, but we can go one step further and take a look at, let's say we want to look at monthly data. We can go ahead and look here, and this is where we actually have the data files. So for today's analysis, we're going to be looking at some atmospheric as well as oceanic output. And so we see at this level, we finally get to see some of the data files that are available. And we see that it's separated by CSM, large ensemble, the experiment, which for these is the 20th century. And we also see the variable name. So if we actually wanted to load one of these into our environment, we'd have to know that entire file path. So we can see our bucket listed here with the component, frequency, and then CSM, large ensemble, the experiment, which we're looking at the future scenario, and then the variable, which in this case, we're looking at T. So you can see we can load that into our notebook. But again, that requires knowing this entire path. It could be relatively challenging to try to look at that. And if we wanted to, let's say we wanted to look at both temperature and specific humidity within the atmosphere, we'd have to write our own little loop here. So we set up our variable list. We're looking at T and Q, which again, our temperature in the atmosphere and specific humidity. We set up our list of data sets we're going to be appending to, and then we loop through using that file path, and then we end up merging it at the end. Which, after calling this together, you'll see that we have our data set. That wasn't too bad, but what if we wanted to look at say the ocean component or other frequencies or so on? We would have to know sort of that entire path again. So we'd have to open up our data set here. So data set. And then we'd have to know sort of that path, which in this case, let's just for example. So this is in a different directory. This is within this ocean directory using monthly data. You can see we're using RCP85 and the temperature. And then we'll also have to pass the storage options. So we can see, so again, that we specified storage options, none is true. We see we got this data set. But you'll notice here that our data is now has different vertical coordinates. We have nlat, nlon instead of lat, lon. So it makes it a little bit more challenging to work with this. And we wouldn't necessarily be able to merge some of these data sets through this loop, and sort of dealing with that is a little bit more difficult. So again, it's difficult to try to find sort of what files we have available and what sort of what's available and merging and all that sort of things. This is where Intake-ESM can come to help. So we're going to use an Intake-ESM catalog that's already been generated for this data set, for this ESM lens data set. This catalog is available via this link right here. So this HTTPS raw GitHub content. So on AWS CSM1 le.json. So the syntax we use here for loading in the catalog, we set data catalog is equal to intake.openESM data store. Then again, we feed it this JSON, which in this case is this AWS CSM1 le.json. So after we load in the catalog, we'll see sort of a summary of our data set. So we have 78 variables. We have 5 different components across 4 different experiments with 6 different frequencies. And to get a little bit more helpful view of this, we can go ahead and take a look at the table. So if we take our data catalog.df, that gives us a pandas representation of the table. So we can see here we have variable, long name, component, experiment, frequency. We have our number of vertical levels, the spatial domain, and so on, along with the start and end time. So we can see this, for example, the 20C runs from 1920 to 2005. So like I mentioned before, we want to look for both temperature in the atmosphere and temperature in the ocean, as well as a couple other variables. So this is a pretty big catalog. So we can use Intake-ESM's search capabilities to be able to subset this. So instead of having to go through and list files and find out what is where sort of on that file system, we can use the search functionality. So the search functionality within Intake-ESM, so you call this .search. And then you basically feed in sort of your query. So say in this case, you wanted to look for temperature in the atmosphere. We want to look for specific humidity in the atmosphere. We want to look at temperature in the ocean, as well as let's say we want to look at salt as well. And we can also search, let's search for monthly frequency. So we can search frequency is equal to monthly. And then let's see what that. So you'll see after, well, first, let's call this. So it's not necessarily going to do it in place. You basically have to assign this to a new variable. So we can call this catalog subset is equal to this. And then we can take a look at our catalog. There we go. So after calling that search, you'll see that we now have 8 data sets, which is quite a bit smaller than our original 56 data sets. And we see that we have 16 assets here. So to get a better idea of sort of what that looks like, let's go ahead and call df. So see here that we have our variables. So we have T and Q across the 20th century, as well as control and history scenarios. And then we also have salt and temperature across all those as well. So across RCP 8.5, history or historical, the control, and the 20C. And then what that means in terms of the, so we see 8 data sets from 16 assets. So as mentioned before, within that catalog specification, so we do group by attributes, you'll see that it's separating by the component, experiment, and frequency. So what that means is, since, say, for example, T and Q of the atmosphere component, 20th century, and monthly, since these all share these group by attributes, they're going to be merged together. And the same applies for the control, historical, and RCPA 5 across both the atmosphere and ocean component. So if we actually wanted to load this data in, we would want to use this 2 data set dict. So let's go ahead. So let's go ahead and load this in. So we could take our catalog subset, and then we call 2 data set dict, which stands for 2 data set dictionary. We'll call this D sets. We will have to pass in 1 additional keyword argument here. So we'll have to pass in storage options is equal to anonymous true. And what this is required when you're working with this Amazon hosted data. So you'll see here that it starts to spit out the keys, and the return dictionary data sets are constructed as follows. So as I mentioned before, it's separated by the component, experiment, and frequency. And then what we get back is this dictionary data sets. So we have the key here, which is that component, experiment, and frequency. So say, for example, ocean dot RCPA5 dot monthly. So we can actually take a look at those keys. This might be a little bit more helpful. So we call dsets.keys. We'll see that we get these different data set keys back. So if you actually want to work with one of the data sets, so say we wanted to work with one of the atmosphere, yes, is equal to, we'd have to pass in our dictionary data sets. We would pass in what key. So let's take a look at the atmosphere control. So we take our dictionary data sets, pass in this key, which again is the component, the experiment, and frequency. We end up with our data set. So at this point, we have our X-ray data set. If we want to look at like the 20th century one, go ahead and do that as well. And we'll see the X-ray data set here. So once it's in this data set, this is typically where you'd want to go ahead and start doing your analysis or sort of working with this data set. But again, it makes it a little bit easier in terms of searching for whatever data you're looking for and sort of getting this extra data set. If we want to look at, say, the ocean data set, we could look at D sets and then follow this same structure here, except instead of passing in atmosphere, we want to pass in ocean. So if we want to take a look at our ocean data set, see how this is there. So we can see we have salt and temperature in there. Again, this can help quite a bit with both searching for whatever data you're looking in for, or just sort of getting it into this extra data set. So one question you might have is how can I sort of get on to writing some analysis code, or how do I write functions to work with some of these? So the 3 sort of basic steps that you want to follow are reading in your catalog, searching for your data, and then calling 2 data set dict, and then finally applying your function across the different data sets. So let's go ahead and scroll back up and look for where we loaded in our catalog. So we'll start off at the same point. So step one is loading in this catalog. So we start with our data catalog again. And then let's say we want to look at temperature and specific humidity within the atmosphere. And let's say we want to look at the 20th century as well as the RCP-85 to sort of look at some of those time series. So we'd set up our catalog subset is equal to our data catalog dot search. And then we start to construct our search. So let's look for the atmospheric component. We want to look for the variable T and Q, not W, T and Q. We want to look at monthly frequency. And then we can also specify the experiment. So we'll do experiment is equal to, and we'll set up a list. So let's look at experiment RCP-85 as well as the 20th century one. So we see that cut down our data sets quite a bit. So we see that we now have two data sets from these 4 different assets. We can take a look at the data frame here, representation, and we see that we have T and Q for the atmospheric component for both the 20C and RCP-85 at the monthly frequency. So one way to sort of see so before this, we sort of knew what variables we were searching for, but if you wanted to search for, so you want to look for, we'll start with these first two. So component is equal to atmosphere, and we want to look at frequency is equal to monthly. You could then look at this table to see which variables you have available. You could also call, this is just pandas data frames, you could call that variable unique, and that would give you a list of the available variables at that frequency. So you can use some of these pandas tricks and that sort of thing to figure out sort of which variables you have available. So now that we have our subset here, we're going to call toDataset dict. So let's load in our dsets is equal to our catalog subset dot toDataset dict. And then we'll want to pass in again our storage options equals non-true. There is some construction going on downstairs. You might hear that in the background. All right, and then you see that we have our two data sets. So we have this 20C atmospheric monthly, as well as our RCP-85 atmospheric monthly data. So if we actually wanted to load in our historical data set, we could go ahead and take a look at that. So using that keys, we have our atmosphere.20c.monthly, and we can go ahead and take a look at the data set. So you'll see that we have all the variables here, T and Q. We have our time that spans from 1920 to 2005, and so on. Then if we wanted to load in our future DS, that would be our D sets, that would be atmosphere.rcp-5.monthly. And then we can see that as well. So we see that we have our future data set is the RCP-85 scenario, which runs from 2006 through 2100. So now that we have these data sets, let's go ahead and just write a simple sort of block of code to take a look at one of the ensemble members, and we will subset for a given location. So let's set our latitude as, let's use Boulder for examples. We know that Boulder's latitude is 40.015. We know that the longitude is 105.275. I looked this up ahead of time. I don't know this off the top of my head. And let's look at just a single variable. Let's look at temperature in this case. So next we want to go ahead and call the X-ray syntax to plot this. So we're going to take our historical data set. We're going to say I select, so this is saying integer based selecting. So we're going to look at the first member ID. We're going to look at the bottom level of the atmosphere. And then, so that what that would give us is just basically a single, you see we have a single vertical level as well as a single member ID. We can also do a little bit more subsetting. So we can use the cell method. This is where we're actually going to pass in the lat and lon. So let's look at, we'll look for this lat and we'll look for that lon. And then we'll use the nearest methods. This is saying that it's going to search for the nearest point. And then we can go ahead and subset for, yeah. So you'll see here, this returns a single latitude, 40.05, which isn't exactly the latitude we were looking for, but it's the closest grid point. We have the bottom level of the atmosphere. We have our closest longitude, which is 105. We have a single member ID, and we have, we're just left over with our time dimension. So for the sake of time, I'm only going to load in the first few times. So let's look at, we'll add one more select here. So we'll add, I select time is equal to, let's grab the first 12 months. And look at temperature. So that's a pretty long line. We're doing a lot there, but this is just basically going to provide a quick plot. Yeah. Oh, yeah. So one good thing to do here before we do this would be to you'll see this issue with the time. So one way to fix this would be, before this, we can go ahead and apply this pre-processing. This is a good practice to do. You get this error, otherwise just make sure you have your CF time installed within your environment. So go ahead and apply that. All right, so you'll see that we have the resultant time series here. We have our temperature along the y-axis as well as our time along the x-axis. We wanted to, yeah. So we can wrap this up into a function if we wanted to. So let's go ahead and write a function to go ahead and apply this plan. So we set up our function. So we'll call this plot point time series. We're going to load in our data set. We're going to load in a specific variable. And then we'll set some default latitudes. So we'll set a default latitude of 40.05. Set a default longitude of 105. There. So those are our arguments for our function. We can go ahead and create a new variable called DS subset, where we're actually going to subset our data set. So this takes in data set. We're going to subset for a single member ID. We're going to look at the bottom level. Let's look at the first 60 times. So this will be the first 5 years since we're working with monthly data. And then we'll also want to select our latitude and longitude. So this is here for our latitude and longitude. And then we'll need to specify our method as the nearest. And then we'll go ahead and subset for just our single variable. As I mentioned before, time can be difficult to work with, so we'll go ahead and set up a function to convert to that date time. So let's do a subset time is equal to do a subset, and then indexes, call time dot to date time index. And then what we want this to return at the end is just this plot. So we'll call subset dot plot, and then we could specify, let's say we want a figure size of, say, 10 by 8. So now that we have this function, let's go ahead and test it out. So we can try this out on this historical data set. So let's pass in historical data set. And say this time we want to look at Q instead of temperature. I'm going to pass that in. So since we already applied that check, we'll go ahead and load this back in. So go ahead and give that a second to load.
Max, while it loads, could you revisit the syntax for decoding CF times? We have 2 questions about it.
Yeah. So the syntax here, so this is some X-ray syntax. So what we're doing here is calling .index as time. So let's construct this way for a second. So if we go ahead and go back to here, so let's go back. So we set up our historical data set. We'll take a look at the time, and you'll see you'll see that it starts off in this CF time. And so when we tried to plot it, you need this, there's some weird matplotlib stuff that's going on here. But one way to work around that is to convert to this numpy or this numpy date time. So if we call this historical ds.indexes time, so that gives us this index, and this has a special method to it where we have this to date time index, which will convert that to this date time index, which makes it a little bit easier to work with. There is a package. There's this CF time package that's made to help this work a little bit easier, but this is sort of just one workaround. So yeah, that's clear.
Perfect, thanks.
Mm-hmm. So again, we pass that historical data set in. That's sometimes the fun of live coding is sometimes things will go wrong. So you'll see that time we weren't converting it's time access. So I actually passed that in. That's giving us a warning saying that converting this summer calendar could lead to small errors. And we get our resultant time series. You can see this time series of specific humidity. So if we actually wanted to apply this to our data sets within the dictionary. At this point, we could go ahead and set up a loop to do that. So we basically write a little loop here. So we want to loop through each of the keys within the dictionary. So let's say we want to do for key in dsets.keys, which again, if we just do dsets.keys here, that returns this our two different keys in our data set, so the 20th century as well as the RCP-85. So we want to loop through those keys. So for key in dsets.keys. And then we'll want to feed each of those data sets into our plotting. So we'll set up our plot here. So our plot is equal to this plot point time series. And as a reminder, this plot time series is a function that takes in an X-ray data set, some variable, and lat and long. So to get our data set, dsets key. And then let's say in this case, you want to look at temperature, and then we'll use the default. That's long. We'll want to pass in plt.show here to take a look at that, and then we'll call plt.close after this to make sure we start off with the new figure every time. So we'll go ahead and loop through and take a look at that. So go back to our dashboard. So you can see it's going ahead and loading in the data, get item, open data set, so on. And so if we go back to here, you'll see that we have our first data set in here. And something that might be helpful here is to actually pass in some additional things. We can add like a plt.title. So let's add in our key at the top. So we can add that. You can add some additional matplotlib arguments or styling. So we can see our atmosphere 20C monthly within that plot. And then we can see our years and our time along the x-axis with temperature along the y-axis. And we'll give that a second. And we also see our future scenario RCP-85 on the other axis. So working with basic creating functions that work at the data set level are generally good practice here and can be helpful working with your analysis. And then one more thing I want to touch on here before we open up for questions. So as a summary, we sort of covered an overview of what Intake-ESM is, how we can use it to search for our data and plot up our data and apply these different analyses. I encourage you to check out the Intake-ESM documentation. So this is the Intake-ESM.readthedocs.io. So you can see a bit about the installation. We have a user guide here that kind of walks you through how to load a catalog and search and work with all those different sorts of things. A good place to check on here, so especially if you're looking for available catalogs, if you go to the frequently asked questions section, you'll see this question: is there a list of existing catalogs? And you can see a list here. So for example, if you're working on NCAR HPC resources, you can see the CMIP6 Glade catalog there in that CDF format. You can see the CSM2 portion of that here, CMIP5. The data set we used today was the CSM1 lens, which is the catalog URL we were using. We also see the CMIP6. This is on the Google Cloud platform through Pangeo and so on. So quite a few different available catalogs. This is a good sort of first place to check to see if there's a catalog for the data you're working with. Another place to check, let's go back to, so I also encourage you to check out, so on the ESDS blog, to go to the ESDS blog here, and all these links are provided at the end of the already pre-run notebook. If you click on intake within the tags, that will pull up all of the Intake-ESM related blog posts that we've worked on through the Your System Data Science Initiative. So say, for example, we want to look at one looking at high resolution observations. We can see an example of using Intake-ESM here. So I encourage you to check out those examples. There's also within the Pangeo gallery, there's a section on working with CMIP6 data with Intake-ESM, which especially when you're working with some of these large ensembles, it could be helpful to be able to search for all those different things. And then the CMIP6 pre-processing. So this is a separate package, but this focuses around using this Intake-ESM catalogs as the sort of core data. So you can see here an example of that. So there's plenty of examples out there, and if you're looking kind of for how to do something, odds are someone else might have an example that's pretty similar to what you're working on. So at this point, I will go ahead and open up for questions. Thank you so much. And yeah, go ahead and ask away.
Thank you so much, Max. That was great. While we wait for questions to come in, I believe you're giving a virtual AGU talk. Would you like to plug that?
What's that?
You're giving a virtual talk at AGU. Would you like to plug that while we wait?
Yeah. So so today we covered the CSM1 large ensemble. Recently, so one project I'm working on is converting the CSM2 large ensemble to those similar ZAR stores and uploading to the cloud. And so, yeah, I'll be kind of giving an overview of that conversion process as well as some of the examples there. So if we go to the Intake-ESM documentation and go to here, we can actually see the, so the CSM2 large ensemble. So yeah, it'll be next Friday during the open science session.
Awesome, thank you. Are you able to see the chat with the questions?
Yeah, so I see there's a question, about the CF time. So yeah, so again, that's sort of this, so one thing to do is to make sure you have NC time access. We apply that. Yeah, so that's a good thing to make sure you have in your environment. I provide an overview of sort of a workaround you should see in there. Yeah, that's sort of one way to, working with times and with some of this stuff can be challenging. Yeah, as long as we have time, I'll go ahead and give a plug. So I mentioned the reason why they need that that decoding, so it has more to do with Matplotlib having to deal with CF time as opposed to date time. They're sort of different objects within Python. So that's what the NC time access provides. That sort of interface with Matplotlib. So ECG tools, like I mentioned, so this is a package for actually building these catalogs. So if a catalog doesn't exist for the data you're working with, you can use this package. Currently, it's mainly limited to CESM as well as CMIP data. But if you're interested in applying this to other data sets, feel free to reach out through this repo, and we could chat about looking at adding additional data sets. Any other questions? Do you expand that question of the trying to load things with different dimensions? Oh yeah, so that's where the group by attributes come in. So if you tried to load two data sets with different dimensions, Intake-ESM will throw an error and not even merge those data sets together. And that's why it's separated. So we just go back to the group by. Let's go back to some of these group by attributes. So this is why like atmosphere versus the ocean are separated by within these different group by attributes. So those wouldn't be merged together. So the group by to check to see what your group by attributes are. So if we have our data catalog, you can search us by calling that group by attributes, and that will feed that back here and sort of tell you what those are. Again, that's something that's specified within the JSON file. Any other questions? Yeah, so you have to know that beforehand. And so that's why, so that's why that's sort of done within the catalog building process. So within this catalog building process, there's an assumption that you know at least a little bit about the data to be able to know what you can and can't merge together. And then in terms of dealing with the length of the time axis, so for example, the length of the RCP85 time axis was different than 20C, so that's allowed. But yeah, you definitely have to test this, so it's good to test out the catalog building and taking a look at some of that to make sure it works with the data and make sure it works with some of those group by dimensions. But yeah, it can be a pretty powerful tool when working with these different analyses more generically. All right.
Thank you. You did a great job, everyone. Flood the chat with thanks before we end the call, and we'll see you all for the next tutorial. So look out for an email on that.
Thanks so much.